lecture 11 of Fundamentals of Communication Engineering. Today we will finish what we started last lecture, so talk about, finish the stuff about probability theory, and then start with noise in analog communication systems. So let me start by repeating a little bit what we talked about last lecture. The main points were, so we introduced a little bit of basic probability theory, but I'm not going to repeat this. But let me start with random processes. So we introduced random processes, which are basically random variables that additionally have a time dimension. So a random variable that depends on time, which means for elements of the sample space, instead of what we get for a random variable, instead of just getting one real number for an element of the sample space, we get a whole function depending on time, a whole real function depending on time. Okay. And then we have seen some results about random processes. So we had some definitions. So we said the family of so all the functions, all the possible functions that this random process can take is called the ensemble. Then we have seen if we fix some time, and then look at all the realizations at this fixed time, we get a random variable. And if we fix instead of time, if we fix the position, so if we fix some function, we get a sample path. And then we have seen that we can define, similar to random variables, we can define a density function, which gives you the density function now depends on two variables, on x and t, and it gives you the probability that this particular x, it gives you the probability that x of t is less than or equal than x. So different from the random variable. The only difference from random variables is that we additionally have this time parameter here. And of course, we can then also, if the density function is if the density function is if we can derive the density function, then we can also define a distribution function by computing the derivative. And then we had some notions like the mean of a random process is now a function depending on t. And then it's just the same as for a random variable. So we fix the time t and then compute the mean. And another thing was we had the autocorrelation function, which is so the mean is kind of the mean is a variable that we get for the time domain, and then we also had something. The mean is something in the amplitude domain, and so we fix some time and look at the mean of amplitudes, and then we also had something similar. So we also had something to characterize a variable to characterize the time domain, which is the autocorrelation function, which is defined that if we take two time points and then take the realizations at those different time points and then multiply them and take the expected value. And then we had some simplification. So we had we wanted to look at the slightly simpler random processes than the general processes. So we defined what a stationary process is. So in this lecture, we only use this notion of Whitesands stationary. So I will skip I will not repeat the first part. But so in our lecture, so when we talk about stationary, it will always be Whitesands stationary. And that means that the mean does not depend on time. So for whatever t we take, we will get the same value. So the mean is just one fixed value, and it means stationary in time domain, which is that the autocorrelation function does not depend on the particular starting point, but only depends on the distance between the 2 points that we take. So here theta is t1 minus t2, right?
Professor, I think you're not displaying the PowerPoint.
I'm not displaying the PowerPoint?
Yes, I think it's just a blank screen for me, at least.
Okay. Maybe I will Restart the recording. Restart the Can you see it now, my screen?
Yes, we can see now.
Okay, great. Sorry. Yeah. Okay. So yeah. So white sense stationary. White sense stationary means so stationary in our lecture means that the mean does not depend on time. So the mean is just for some fixed real number, which doesn't depend on time. So for any time we take, the mean will be the same. And stationary in time domain, which means so stationary in time domain means that the autocorrelation function does not depend on the particular point where we start, but just depends on the difference between those two times. So the autocorrelation function is just a function of tau, where tau is the difference between t1 and t2. And then we also had the notion of ergodic process. So an ergodic process simplifies things a lot, because for ergodic processes, we usually don't. So the problem with this general random processes is that we get different. We get so each experiment has a different function as an output, and we get infinitely many different functions that we have. If we want to, for example, to compute the mean, we have to take infinitely many realizations and take the mean from them. Or at least generate, if we want to approximate the mean, at least generate many, do many experiments and then take the mean for fixed times. And we usually cannot do that. So we only have one particular, we only have at mostly one. So mostly we only have one realization of the function and can compute, for example, the time mean of this and so on. And for ergodic processes, this usually is enough, because for ergodic processes, again, let me not repeat the general definition, but only talk about white sense ergodic. So for white sense ergodic processes, they are defined that the mean, if we take the mean in the time domain, so this is just defined as by, so this is just the limit for t to infinity of 1 over t times the integral of x of t. So the mean that we would get in the time domain is the same as when we take the mean in the amplitude domain. So if we take the if we compute the mean by taking the mean from the amplitude domain, and the autocorrelation, and a similar result holds for the autocorrelation function. So instead of taking realizations at different times, we can take one realization and then compute kind of the autocorrelation function using different time points in this realization. So the definition of the autocorrelation function simplifies to this expression. So the limit for t to infinity of 1 over t times the integral of t, the integral over t of xt times xt plus tau. And ergodic is a stronger notion than stationary. And usually we will assume that random processes we look at are at least white sense ergodic, because that simplifies the analysis a lot. Okay, so this was the repetition of last lecture. Are there any questions? If not, then I will go on with defining the next notion, which is so what we want to do now. So now we have seen random processes, and we have seen so random processes. If we take one realization, so if we take one experiment, we will get a function of time. But what we also want to do is we want to look at random processes from the viewpoint of the frequency domain. So the same what we have done for if we had a deterministic if we had a deterministic signal, we took the Fourier transform, and then had this duality between time domain and frequency domain, and we want to do something similar for random processes. and this is so the notion we get is called power spectral density. And before I give you the formal definition, let me just introduce the idea behind behind this notion of power spectral density. So the idea is we take so we have some random process X. Let me maybe make this. So we have some random process X, and then we can take, what we can do is take different realization. We can look at different realizations of this process. So if we take a realization, if we take a sample pass of this process, we get a function of time. So this would be x1 of t is some function of time. Somehow looks like this maybe. Then we can take another realization, get another function of time. Maybe it's a little bit faster. It would be x2 of t, and so on. Can look at several realizations. And the idea is now, well, the idea is we would like to take the Fourier transform. So on this side, we would like to take the Fourier transform of those realizations, but usually or often this the Fourier transform won't exist, because we have seen in the Fourier transform lecture that we usually assumed that we have energy signals, so that the processes have finite energy. But if we look, most random processes we look at, if we take some realization, they will have infinite energy, and we cannot compute the Fourier transform. But what we can do is we do something similar as when we were going from Fourier series to the Fourier transform. We finish some fixed time period. So let's say we take some interval around 0 of length t, and just cut everything. So just take the function inside this interval and set it to 0 outside of this interval, so that we get a energy signal. So what this means, we multiply. So formally, this just means we multiply by the rectangle function, right? We multiply by this function, by a rectangular function of length t. And so we do this also here and here. And then if we look at this, if we call this x1 t of t, so the function restricted to an interval of length t, we call the realization restricted to a time interval of length t, we call x1t, x2t, and so on. And all those functions, so those functions now will have a Fourier transform, right? Because they are finite functions, and we can compute the Fourier transform of them. So let's look at the Fourier transform of them. So on this side, we look at the Fourier transform of each of those functions. So so here we get capital X1 t of omega, which maybe looks somehow like this, and so on. For the other ones, we do the same. So we get Fourier transforms here, and then what we do, instead of just taking the Fourier transform, we look at the average power that we get for each frequency. So over this time domain. So what we do is we take the absolute value of x1 t omega. So this is kind of, we can call the power of omega is x1 of t of omega squared divided by the length of the time interval. So divided by t, and we do the same here. And so on. So we compute those values, and the power spectral density of this function, so the power spectral density of this random process, is now a function of omega that is defined as the expected value so, well, not yet, but so then what we do is then we do the same as what we did with the when we looked at the Fourier transform. When we went from Fourier series to Fourier transform, so we let t go to infinity. And then what we do, we define the power spectral density of this random process. As what we get when we take the expected value of all those, right? So this is the definition of the power spectral density. Or this is the idea behind the power spectral density, and I will give you the formal definition on the next slide. So what is power spectral density? So power spectral density is a representation for random processes in the frequency domain. And so this is just what I just did. So we take sample functions and then define a restriction of the sample. So restrict the sample function to some fixed time interval t by multiplying by the rectangular impulse function. And then we can compute the Fourier transform of this. We can compute the Fourier transform of this function, and the power spectral density is what I just said. So we take the limit of t to infinity of 1 over t times the expected value of what we get if we take so the expected value over all those Fourier transforms of the realizations of the random process. Okay. Any questions for the definition? So this is the formal definition of the power spectral density of a random process. Okay, and then we will also see. So I will give you one important theorem. So one important fact about the power spectral density, because there's a quite for stationary processes. For stationary processes, there's a simple way to compute the power spectral density, and I will just give you the result without any proof here because we are running a little bit out of time. So I will not do the proof of this important theorem, but still it's quite important. So the theorem is called the Wiener-Kinschinit theorem, and the result is just the Fourier transform of the power of the autocorrelation function. So this is the autocorrelation function of the random process, right? So the Fourier transform of the autocorrelation function gives you the power spectral density. So this is the relation between the power spectral density and the autocorrelation function. And we will use this theorem lots of times. Okay. Now let me also prove some other results. So this is so for an ergodic process, we can so this gives us a simple way. So this gives us a simple way to talk about the power of an ergodic process. So so from now on, all processes we will so one thing is so we only look at real processes, right? Only look at real valued processes from now on. So this will for all the remainder of this lecture, this will hold true. We will only look at real valued processes. We will not look at complex valued processes anymore. And then we can compute the power of so we can compute the power of one realization by taking just the formula that we had for the power, right? So 1 over t times the integral over t of xt squared dt. But this is the same as taking 1 over t times t. So just writing xt squared as xt times xt plus 0. But what is this? Well, this is just this is just the autocorrelation function at time 0, right? So the power of an ergodic the power of a process, the power of a random process is just given by taking the random the autocorrelation function at time 0. And well, we will now show something similar to what we have already seen for when we talked about the Fourier transform. So the what we call Parseval's theorem. So Parseval's theorem is that instead of computing the power in the time domain, we can also compute the power in the frequency domain, right? And we will now show something similar. So why is this? So we have seen on the last slide that the Fourier transform of the autocorrelation function is the power spectral density. So what does this mean here? So that means we can write. That means we can write the power spectral density also as the inverse Fourier transform of the power spectral density. So this is 1 over 2 pi times the integral from -infinity to infinity of the power spectral density times e to the I omega t, the omega. So this is just the inverse Fourier transform. And then using that the power is just the autocorrelation function at time 0 for tau equals 0. So we can write the power as 1 over 2 pi times the integral of the power spectral density. Right. So we get the power. We can, instead of computing the power in time domain, we can always compute the power in the frequency domain using this formula. Okay. And what we want to do now is we want to talk about noise. So we want to use random processes to define noise. And we will look at in this lecture, we will look at only one kind of noise, the simplest kind of noise. So what is called white noise. And a white noise process is defined as that all frequency. So we will define the noise as having the same power for all frequency components. So that is what white noise is. So all frequency components have the same power. So formally, what that means, a white noise process, white noise process omega t, wt, is defined as having power spectral density some n0 half. So n0 is just some real number, and we define the power spectral density of the white noise process has the same power for all frequencies omega. And we use n0 half because we want to we want to assign half of the power to positive frequency. So the idea behind taking n0 over 2 is assigning half of the power to negative frequencies and half of the power to positive frequencies, because basically negative and positive frequencies are the same frequency, right? So we say, so what the idea here is that each frequency has power n0, and we assign half of the power to negative and the other half to positive frequencies, right? So this is just the definition of a white noise process. A white noise process is a process where the power spectral density function has this form. So it's constant. It has some constant value for all omega. And then we can use what we have seen. So we can use our previous result to compute the autocorrelation function of the white noise process. So the autocorrelation function of the white noise process is then given by the inverse Fourier transform of the power spectral density, and we have seen what the inverse Fourier transform of a constant function is. So we will just get n0 half times delta of t, where delta is the unit impulse function, right? So we will the autocorrelation function will look will be 0 everywhere and will kind of be infinite at 0. And what that means is, well, this is kind of what we expect, right? What we expect when we define white noise, because we want to have that no matter how close, no matter how close no matter how close two times are together, the noise at different times will be completely non-correlated. So if we so if we take any two time points, then we will have completely independent, non-correlated noise. Right. So this is what the white noise process is. Any questions so far? Okay. One thing about this white noise is if we compute the power of the if we want to compute the power, so we just have seen that the power is given by the integral over the power spectral density function, but this will be, since this is since we have the same power over all frequency components, well, the power of this will of course be infinite. So what we will do is we will never look at the noise at the whole frequency domain, but we will always first filter out the frequencies that we don't need. So we will always only look at filtered noise. And this is so if we use a baseband filter, so that means a filter where we filter out frequencies centered at 0 with some bandwidth b. So we filter out all frequencies that are higher than that are higher than b hertz. Set them to 0. Then we can look at what if we have a white noise process. What will happen if we apply such a filter? So if we just remove all frequencies higher than some fixed bandwidth. So what will be the so we filter out all the higher frequencies. So that means the power spectral density will just be n0 half times the rectangular impulse function of omega over 2p over 4, actually 4pb, right? So we will filter out everything outside here and outside here, and then we can calculate the autocorrelation function by taking the Fourier transform. So we have seen what the Fourier transform of the rectangular impulse function is in the Fourier transform lecture. So this will be just n0 times b times the sinc function at 2p b tau. And then we can compute the power by taking we can compute the power of this process, of this baseband filtered white noise process, by taking the autocorrelation function for tau 0, and this will just be n0 times b. So this is the result. What we get for baseband white noise is that the power of this noise will be n0 times b. And now, but this is not the only kind of filter that we use. So usually what we do is, so next we want to talk about modulation. So we have seen in modulation, we change the frequencies, right? So we will not, we change to some higher frequencies. So we will not be centered around 0, but we will have some frequency. We will have some frequency omega c and minus omega c, and we will look at the filter that filters out frequencies with some bandwidth centered around those 2 points, omega c and minus omega c. So let me just tell you what happens here, because the proof is a little bit more complicated. So we will skip it here, but it can be shown. That in this case, the noise process that we get, so this filtered noise, the filtered noise process that we call n of t. So after applying such a bandpass filter, can be separated into two components. a cosine component NC of t times cosine omega c of t, and a sine component plus, minus ns of t times sine omega c of t. So we can write this filtered process in this form where nt and ns are baseband white noise processes. So that means we can NC and NS of T are baseband white noise processes, like we have just seen. So they are of this form with the same bandwidth that we take here. So we can kind of separate. We can split up the noise process that we get into two baseband white noise processes with the same bandwidth. Okay, and then we have already seen what the power spectral density of those processes will be. So they will have the same power spectral density. Right. So we can write those moved power spectral densities by just adding the power spectral densities of the the original noise process and then filtering out everything that has frequencies larger than 2pb. And then we can compute the power. So what we will get is that the power of all of those processes, so the power of NS will be the same as the power of NC, and this will be the same as the power of the whole bandpass white noise process. And we can show. So I will not really show this, but I will just give you the end result, which is that it will be 2 times N0 times B. Right. So this is what we get. This is what we get for the power of the bandpass white noise process, and we will use this many times. And we will also use this relation many times in the lectures from now. Okay. Any questions? No. Then so this is kind of the end of the probability series stuff. And next we will apply this to communication systems. So we will now look at all the analog modulation schemes that we have seen in the previous lectures, and then and see how they behave when we additionally add noise. So what we will use now is the model for noise that we will use in this lecture is always the same. So we have some signal. So now both signal and noise. We have signal and noise, and both will be random processes, right? And we assume that both noise and signal have zero mean. So for the signal, usually, so for the noise, this is kind of well, for both signal and noise, we usually don't. If they don't have zero mean, we can just apply some. We can apply some filter that filters out the DC component. So if the mean is just the DC component, and if the mean is not zero, we can filter that out. So we can always assume that that noise and signal both have zero mean, and we will assume that the noise is always a white noise process. So we have seen what that means. So that means that the autocorrelation function is for some fixed N0 is the autocorrelation function is given as n0 times the Dirac delta function of tau, and well, the same, just by taking the Fourier transform, is that the power spectral density, so the power for all frequency components for all omega, the power for all omega is given by n0 over 2. So the power spectral density of omega is n0 over 2. And then, well, a communication system. So the first thing what we will do is we will filter out all the so there will be things at all frequencies, right? So if we send something over a channel, there will not be our signal will have some frequency components, right? And there will be other so there will be other stuff there will be stuff at all kind of frequency components. There will be other stuff, there will be noise, and there might be other processes at the other frequency components. So the first thing every communication system has to do is apply a bandpass filter so that we only look at the frequencies of our signal we're very interested in. So filter out all the unnecessary frequencies. And that means we also filter out, so we will also always have bandpass white noise. So we filter out the noise that is outside of our frequency ranges. And that means the power of the noise will always be given by n0 times b, where b is the bandwidth of the bandwidth that we use for the limitation. So the bandwidth where our signal belongs to. And then what we do is after applying the bandpass filter, we have some filtered signal, and this will be put to the demodulator. So then we will look at our modulation schemes and take the demodulation schemes that we have seen in the analog modulation lecture and put this filtered signal in. And then we have to look at what happens if this signal what happens to the noise in the demodulator. And then we will get an output signal, and we have to relate this output signal, which is now given by the signal together with the noise, and have to look at how much the noise has impact on this output signal, right? And the noise we look at will always be additive. So it just means we just add the noise will just be added. So our model for the signal with noise is just we add the noise to the original signal. This means additive noise. Okay. And then to kind of quantify this relation, so to quantify how good a communication system is, when we also have noise, is we define something which is called signal to noise ratio. So this gives you the signal to noise ratio gives you the power of the signal divided by the power of the noise, right? So how much stronger is the signal? So how many times stronger is the signal than the noise? And we will define two signal to noise ratios at two different points in the communication system. So first, let me give you the definition of the signal to noise ratio. So the signal to noise ratio for a random process, for a communication system where both signal and noise are random processes, is given as the expected value of the signal squared times the expected value of the noise squared, right? So this is basically what we get if we use the formula for the power, right? So basically this is the power of the signal divided by the power of the noise, but both signal and noise are random processes here. And now we will define, now what we want to do is we want to look at the signal to noise ratio in a communication system and then use this as a measure on how good the communication system is. And we will, to do this, we will look at the signal to noise ratio at 2 points. So first is the signal to noise ratio at the input of the receiver. So the receiver is the part that will do the demodulation and so on, right? So first is the signal to noise ratio after we send it to the channel and after we apply the bandwidth, the filter to only look at the bandwidth we are interested in. So this is the signal to noise ratio at the input. So we will have some signal at the input and some noise at the input, and then we can compute the signal to noise ratio at the input, and then we will put this signal together with the noise to the receiver. Then the receiver will do some processing of this message, and then we will get some message at the output, which also has some signal component and some noise component, and this will be the signal to noise ratio at the output. So then we can define the signal to noise ratio both at the input and at the output. And what we want to do is look at how the signal to noise ratio improves from input to output. So we want to compute the signal to noise ratio at output as a function from the signal to noise ratio at the input. So how much does it change, and then what parameters does it depend on? And the other thing we want to, so we usually want this to improve a little bit by doing the things that the receiver does. And the other thing we want to look at is we want to compare this to we want to compare our modulation scheme to what would happen if we just send the message without doing any modulation. So just send a message with the same power through a channel. Don't do any modulation. So just use a baseband channel, and then compute the signal to noise ratio, and then look at how much worse or how different the signal to noise ratio for the modulated for the output of the modulated signal is to the in comparison with the signal to noise ratio for the baseband system. And before we do this, we will actually compute the baseband system signal to noise ratio. So a baseband system just means we send a message with some fixed power. So we usually use to compare with the modulated system, we will send the message signal with the same power as the modulated wave. So the modulated wave will have some power, and we will look at the signal that has the same power as the modulated wave, then send it through the baseband system, which just means we just send it without changing the message at all. We send it through the channel. Then there will be some additive white noise. So there will be channel noise that we add. And then we filter out. We use a low-pass filter with the bandwidth equal to the message bandwidth to filter out all the components that we don't need. And then we get an output message, which will be the message together with the filtered noise, right? And we have already seen what happens. So we can compute the signal to noise ratio here at the output. So for this, we first have to compute the power of the noise at the output, but we have already done this, right? So this is just this is what we did here when we talked about baseband white noise, right? So we use a baseband filter to filter out all the frequencies higher than B hertz. And then we have computed what the power of this noise is. So the power of the noise after applying this filter, the power of the output noise will just be N0 times B, right? This is what we said. This is what we said here. And we also have to compute the power of the output signal, but the power of the output signal is just the input signal. So the power of the signal at the output here will just be, because we didn't do any modulation, so the power doesn't change. So it will be the power of the input signal, which is just the power of the message. So our reference, so the signal to noise ratio at this output, which we will use as reference to compare to for other modulation schemes, which is why we will call this reference signal to noise ratio, is just the power of the message over N0 times B, right? So this is the signal to noise ratio for the baseband system, and when we now look at our modulation schemes that we have seen in the modulation lecture. Then we will compute the signal to noise ratio for the modulation scheme, and then compare to sending a message with the same power as the modulated signal. So the power here will be the power of the modulated signal, and divide by this factor n0 times b. Divide by this factor and compare how much was the modulated signal, how much was the modulation scheme is in comparison to the baseband system, in comparison to when we don't do any modulation at all. Or how much better. Okay, so this is what we will do now for the remainder of this lecture. We will go through all the modulation schemes that we have seen, and then compute the signal to noise ratio of them. So the first one is double sideband suppressed carrier amplitude modulation. So this was, if you recall, this was the simplest form of modulation. So recall that modulation was just multiplying. So in amplitude modulation, we just encode the message in the amplitude of the carrier. So we had this carrier function. Carrier function was sum factor times cosine omega ct. And then we just double sideband suppressed carrier was just multiplying the message signal with this carrier function. And for simplicity, we use here as carrier function square root of t times cosine omega ct, because then we will have the same input and output power. This is also something we have seen in the modulation lecture. That when we just take cosine omega ct, we will have a signal of half the strength in the end. But if we multiply by square root of 2 in the carrier, we will get a signal with the same power in the end. So how does our modulation scheme look like with noise? So first we take the message, then multiply by square root of 2 times cosine omega ct. Then there will be we will send this through the channel. There will be some noise that will be added to this message. Then we apply a baseband filter, because we have seen that the frequencies in double sideband suppressed carrier, so the frequencies do not change. The frequency range doesn't change, but we will get copies of the message signal that are centered at omega c and minus omega c. So the bandpass, we will apply a bandpass filter that filters out frequencies of bandwidth b around this frequencies with bandwidth b around omega c and minus omega c, which will then contain our original message and the noise that we have at those frequencies. And this will be the signal after filtering will be the input signal to the receiver. So this will be the input signal y to the receiver, and the receiver, the demodulation scheme we have seen in double sideband suppressed carrier is just doing the same modulation again. So what we will do is again multiply this new signal y of t by square root 2 times cosine omega c of t. Then we will get back we will get back our original signal and 2 copies of this that we don't need. So we then apply a baseband filter to just filter out our original frequencies, and then we will get the output of this the output message of this modulation scheme. And now we will compute all those numbers that are written here. So let me just write this down. So the input signal the input signal what we get here, what we send through the channel, so as in, the input signal is just square root 2 times mt cosine omega ct. And we assume that we have, so the noise, we will get the filtered noise. The filtered noise, the noise we will get is just what we have seen. So is bandpass white noise. And bandpass white noise we have seen in the definition when we define bandpass white noise here. We can write it in this we can use this result and write it in two components. So write it as NC t cosine omega ct minus ns of t sine omega ct. And here both, so here NC and NS are baseband white noise. Okay, and this means our input signal. So what is the input signal? So it's the field. It's the field. It's the input process. It's the input signal plus the filtered noise. So y, the input y that we will give to the receiver is given by this formula, right? So the input signal plus the input noise, and well, we can just compute this. And now let us compute the different signal to noise ratios. So go to the next slide. So let me first compute the signal to noise ratio at the input. Okay, so what is the power of the input signal? The power of the input signal is the power of the modulated signal. So this is the power of square root of 2 times mt cosine omega ct. And we have already seen what this is. This is just the power of the message. Right? And what is the power of the output signal? Sorry, what is the power of, not the power of the output signal? What is the power of the input noise? Well, the noise here is just the bandpass white noise, and we have computed its power here. So the power is 2 times n0 times b. So the power of the input noise is 2 times n0 times b, and that means the signal to noise ratio at the input, the signal to noise ratio at the input of direct sideband suppressed carrier is just the power of the message over 2 times n0b. Okay, and now let us compute the signal to noise ratio at the output. So let us first look at the output function that we get before filtering. So let's call this y pre. So this is what we get. This is what we would get here before filtering. Before applying the bandpass filter, we just get sorry, not here. Before applying this filter, right? So we want to look at the output before filtering. So here, right? So this is y out before applying the baseband filter is here. So after doing the first step in the demodulation, we'll just be multiplying our input signal. The input signal is given by this, and then multiplying our input signal by so doing this first step here, which is multiplying the signal by square root of 2 times cosine omega ct. So taking the input signal and multiplying by cosine omega ct and multiplying by square root of 2. And then we have seen that we can write the input signal as the sum of the input noise and the output noise. So what we will get is this. So this is the input signal. Then we have our bandpass noise, which we have seen as NC of t times cosine omega ct minus NS of t times sine omega ct. And then we take all of this and multiply all of this by square root 2 times cosine omega c of t. So this will be our output signal before we apply this baseband filter, and the baseband filter will filter out all frequencies that are higher, that have higher, all frequencies higher than our message frequency B. So instead of calculating all this, instead of calculating all this, let me just remind you of some trigonometric identities. That we can use for simplifying this. So we will use that cosine omega ct squared is the same as 1/2 plus 1/2 cosine 2 omega ct, and cosine omega ct times sine omega ct is the same as 1/2 sine 2 omega ct, right? So we will use those identities, and now let's look at what happens to the signal after filtering. Okay, so now we apply the filter, which means all components that will have frequencies higher than the bandwidth of the message signal will be filtered out. So let's look at what happens. So let us first look at the first component. So multiplying this with this, what we will get is, well, since this is cosine squared omega ct, we will get 1/2 plus 1/2 cosine 2 omega ct times the message signal. But so the first component will just be the message signal plus m of t times cosine 2 omega ct. But this has already frequencies around 2 omega ct, right? So this will be much higher than the bandwidth of the message signal, because well, that was always our assumption, right? That omega c is much higher than all the frequencies that appear in the message. So 2 omega ct, well, we will not, if we apply a baseband filter, this component will just be removed. So we don't have this component. And well, the same is then, let's look at multiplying this with this factor. So what do we get? Well, it's the same. It's cosine squared again, but here we don't have the factor of square root 2. So what we will get is 1 over square root 2 because of this 1/2 here, times the cosine component of the noise, and then again plus something with frequency times cosine 2 omega ct. But again, since those frequencies are much higher than the bandwidth that we allow, this will be filtered out. So the remaining, the second term here will not appear. And what happens with the last component? So let's just look at this component too. So this is sine omega c times cosine omega. So if we multiply this by this, we get sine times cosine. So this will just be 1/2 sine 2 omega ct, and this has frequencies much higher than those that we filter out. So this will disappear. This will disappear completely. So as our output message signal after filtering, we will get this expression, right? So y out is m of t plus 1 over square root of 2 times the cosine component of the noise. Okay, so let me write this again. Okay, and now we want to compute the signal to noise ratio at the output. So what is the signal part? What is the signal? So this is the output message, and well, it's clearly separated into a signal part, which is m of t, and a noise part, which is this. So we can easily separate this into the signal at the output, which is just m of t, and the noise at the output, which is 1 over square root of 2 times the cosine component of the noise, so nc of t. So what is the power of the signal at the output? Well, the signal at the output is just a message signal, so this will the power of the message. What is the power of the noise at the output? Well, we have seen this. So this will be just 1/2 of p of the cosine component of the noise, and we have seen what this is in this when we looked at bandpass white noise, right? So the power of each of those components was 2 times n0 times b, and this means half of this is just n0 times b. So now we have the signal to noise ratio at the output for DSB SC is just the power of the message over n0 times b. And this is 2 times the signal to noise ratio that we had for the input, right? So after the receiver, we will improve the signal to noise ratio by a factor of 2 because we filter out all those higher frequencies that have additional noise. So we filter out some noise, so we will improve the signal to noise ratio by a factor of 2. And now let's also compare this to the baseband system. So comparison. Comparison to the baseband system. Comparison to the baseband system. So what did we have as the power? The power of the modulated signal was just the power of the message signal, right? And so it has the same power. So for our reference system, our reference baseband signal system, we have the power of the message, because this is the same as the power of the modulated signal, over n0 times b. And this is just the signal to noise ratio, the same as what we got, right? So using this modulation scheme, we do not lose anything in comparison to the baseband system. So we have the same signal to noise ratio as if we would use the baseband system. Right? So from the signal to noise perspective, this is exactly as good as the baseband, as not doing any modulation at all. But we have seen that there are some problems in the modulation lecture. We have seen that there are some practical problems with implementing this modulation scheme. This is why we have looked at other modulation schemes, and now we will look at the next one we have looked at in the modulation lecture, namely direct sideband full carrier. So recall that the problem with direct sideband suppressed carrier. The problem with direct sideband suppressed carrier was that we don't have the carrier, so we don't send the carrier with the message, and that means we have to generate the receiver also has to generate a carrier signal with exactly the same frequency as the sender of the message. And this is usually quite difficult to realize. So because of this, a simple demodulation will be simplified or will be made cheaper if we also send the carrier additionally to the message. And this modulation scheme was called direct sideband full carrier, and we have seen that the recognition. So what we can do then to reconstruct instead of doing the coherent reconstruction, which means just applying the modulation scheme again. There's a different form of demodulation that we can do, which is envelope detection. And recall the envelope was just so the envelope of the carrier signal was just the peaks of the amplitude. And we have seen that if the message that we send, if the modulated message that we send does not intersect the x-axis, so if it's always larger than 0, then we have seen that we can use envelope detection. For demodulation. And an envelope detector we have seen can be implemented quite cheaply. So all we have to do is reconstruct the envelope of the signal we send in the demodulation. So the demodulation scheme now looks different, and the message we send looks different. Okay, so how did this look? So now the input message we send, the message that we will send out through the channel will not be just mt times cosine omega t, but it will be some factor a plus the message signal times cosine omega ct. So instead of just multiplying the message, we make the message larger by some factor a, which is large enough such that the message will not become negative, and then multiply by the carrier function. And the assumption here is that a has to be larger than the peak message signal, which was the maximum of the absolute value of all possible messages that we can send. So this a will always be larger than all possible points all possible values that the message signal can take. Okay, and for the noise at the input, we will use our bandpass white noise model again. So this will again be nct cosine omega ct minus nst sine omega ct. And now let us compute the signal to noise ratio at the input. So what is the power of the input signal? Well, the power of the input signal is now this is what we have seen in the previous lecture, so I will not repeat it. I will just give you what the power is. The power is a squared plus the power of the message half, right? And the power of the input noise is what we have always used in this lecture. So what we have shown in the previous slides is 2 times n0 times b. So this is the power that we always have for bandpass white noise, which means that the signal to noise ratio at the input for direct sideband full carrier is a squared plus pm, the power of the message signal, times over 4 n0 times b, right? So just the power of the signal divided by the power of the noise. Okay, so this is the signal to noise ratio at the input, and now let's compute the signal to noise ratio at the output. Okay, so the output is the envelope of the envelope of the input signal, right? So we have this input signal, which is just the signal plus the input noise, which is just A plus M of t plus NC of t. So I write it a little bit differently, but times cosine. So we have those cosine omega c t components minus ns of t times sine omega ct. So this is just what we get if we add our bandpass white noise to our input signal. So the input signal was just A plus mt times cosine omega ct, and the white noise, the noise that we get was nc cosine omega c minus ns sine omega ct, right? And what our envelope detector will output is is the peaks of this sinusoidal wave. So to see what to simplify this, let us use the following. So we will write this now in polar coordinates, and for this we will use the following trigonometric identity that we have used many times in this lecture. So we will use that A times cosine alpha plus B times sine alpha can be written as square root A squared plus B square root A squared plus B squared times cosine alpha minus theta, where theta is arcus tangens B over A, right? So we have used this several times, and we will use it again now. So this means we can simplify, or we can rewrite this expression as E of t times cosine omega ct plus theta t, and E of t and theta of t are defined by this identity here. So they are defined like this. And but what we are interested in, what our envelope detector. So this is again a sinusoidal function, and our envelope detector will just output this E of t. So we are only interested in E of t, and we can forget about theta of t. Right? Okay, so what is E of t? Well, E of t is this factor in front of cosine squared plus the factor in front of sine squared. So what we will get is we will get A plus mt plus nct squared plus ns t squared and the square root of this. Okay, and now, well, this is still quite complicated, so we make one assumption that simplifies things a lot. So the assumption we make is, but basically it's that the signal to noise ratio at the input will be a large number. So what we assume is that this factor A will be much larger than the noise components, right? So it means our signal will be much stronger. So we send a signal that is much stronger than the noise in the channel. And this is kind of a realistic assumption, right? Because well, if we send a very weak signal that is not much stronger than the noise, we cannot expect to have that good results, right? So we usually assume that we send a signal that is maybe 1,000 or 10,000 times as strong as the noise in the channel, just to be able to reconstruct anything at all. Okay, so this is our assumption, and if we have this assumption, well, we can assume that this is basically 0. So we can assume that E of t is approximately just the square root of this first, the square root of the square of this first factor. So we will just get a plus m of t plus nc of t, right? So this is what e of t is, and well, what will be the output? The output of our demodulation scheme will. So what the receiver will do is it will additionally remove this constant factor a. So it will just subtract a. So we have y at the output is just m of t. So y at the output after noise is just m of t plus nc of t. Okay. So y at the output is just what I just said, m of t plus nc of t, which is actually exactly the same as we had seen in the double sideband suppressed carrier scheme. So we have already computed this. The power of the signal at output is this m of t. The noise at the output is nc of t. So the power of the signal at the output, is just the power of the message. The power of the noise at the output is 2 times n0b. And then we get the signal to noise ratio at the output of DSB full carrier is just the power of the message divided by Tn0 over b. And we can rewrite this a little. So recall that the signal to noise ratio at the input, what was the signal to noise ratio at the input? The signal to noise ratio at the input was this expression, right? So a squared plus pm over 4n not b. So what do we get for the signal to noise ratio at the output? It's 2 pm over a squared plus pm so this factor times so this is the factor that we will get for this factor we will get for multiplied by the input by the signal to noise ratio at the input. Right. And so how good is this? Let's also before we say this, let us also compare to the baseband. So compare to the baseband system. So let's do the comparison to the baseband system. So recall that we want to compare with the baseband system when we send a message with the same power as the modulated signal. So what was the power of the modulated signal here? That was the power of Sin was pm squared, sorry, not pm squared, but pm plus a squared over 2. So this is the power of the message that we send through the channel, right? And we want to compare what happens if we send a message with the same power through the baseband channel, where we don't do any demodulation. Then we had that the signal to noise ratio was just this power divided by n0 times b. So the signal to noise ratio of our reference system is pm plus a squared over 2 n0b. And let's see what is our the factor that this modulated system is worse than our baseband system. So divide the output signal to noise ratio of our direct double sideband full carrier modulation scheme by the reference, by our reference signal to noise ratio, and what we get is, well, if we divide this, we just get PM over A squared plus PM. And well, we have, so how good is this? Well, even in the, so how do A squared and the power of the message signal compare? Well, we have seen that A squared always has to be larger than the peak of the message signal. So in the best case, in the best possible case where we have modulation index 1, then A will just be the peak of the message signal, and well, the power of M will always be smaller than the peak of the message signal squared, right? So even in the best possible case, this will be less than or equal than 0.5. And this is only for messages that always take the peak message signal, and when we have modulation, index 1. So this modulation scheme will be much more will be much more sensitive to noise than our baseband, than our non-modulated system. So this will be much more sensitive to noise. And the reason for this is that we use lots of power. We have seen this in the previous lecture, right? We use most of the power to send. We use most of the power to send the carrier and not the message signal. So all this wasted power will generate some additional noise. Will be responsible for some additional noise. And we will get this additional noise after filtering even, and then we will have a system that is more sensitive to noise than our original system. Any questions so far? If not, then I will go on with. So I will start a little bit to talk. So we will not finish this lecture, but I will start talking a little bit about noise in angle modulated systems. And what we will do is, we have seen that we have seen different types of angle modulation, but for time reasons we will only look at the noise in FM, in frequency modulation. Well, the reason for this is one reason for this is that the phase modulation. Phase modulation is we have seen is just doing frequency modulation and additionally computing the derivative of the message signal. So it's just one additional derivative, and then the derivation is basically the same as the derivation for PM modulation under noise is basically the same as for FM modulation. So we will, in this lecture, we will focus on only doing FM modulation as an example for noise in angle modulation. Okay. So one thing about FM modulation that we have seen is that in angle modulated systems, the bandwidth that we need to the bandpass filter here, so the bandwidth of the message we send through the channel will be larger than the bandwidth of the original signal. So we have seen some relations how the bandwidth compares to the original bandwidth of the message signal, and we have seen that for angle modulation actually the bandwidth will be infinite, but we can approximate it by 2 times the bandwidth plus some factor that depends on the modulation index, to get which will be enough to send most of the message power, and the other components will not have a very high impact on the overall message. But the bandpass filter here will not filter frequencies with frequency range B, but it will have some different frequency that we call transmission frequency. So the transmission frequency will in general be different. The frequency that we use for transmission will in general be different from the frequency that we use that the original message signal has. Okay, so BT is the transmission. And our bandpass filter filters all. So this bandpass filter filters all frequencies in the range omega c plus minus p times b of t. So this is how the bandpass filter works now. And then well, we can. Let me finish by just writing what input signal and input noise are, and maybe the input signal to noise ratio we can still do quickly. So the input signal in FM modulation, what was the signal that we sent in FM modulation? It was AC times cosine. So AC is just some constant for the carrier that we use. So the carrier will have constant amplitude AC, and then we modify the frequencies, and we have seen that we can write this as phase. So we have some modulation. We have some modulation factor KF, and then take the integral of the message signal up to time t. Right. So this is the expression that we had for frequency modulation. So this is the expression we had for frequency modulation when we talked about frequency modulation a few lectures earlier. So this is just the input signal. Well, technically, it's not exactly the input signal because, well, this is what we will get. This is the input signal we will get after the bandpass filter, but we assume that our transmission frequency is high enough such that this is a very good approximation already on our message signal. Right? So we filter out some higher frequencies that might be in this term, but they don't contribute much to the original signal. So we can use this as an approximation. And let me also give you the noise at the input. So this is again our bandpass white noise assumption. So this we can just write as NCT cosine omega CT minus NST sine omega CT. And now, well, NC and NS are baseband white noise. Baseband white noise, but with those frequency range, with frequencies BT, right? With frequency filter BT, right? Because we filter in the range of the transmission frequency, not in the frequency of the original message, which we call B. Okay, so let me finish this lecture by giving you the input signal to noise ratio, and then we will continue with the rest next Wednesday. So the input signal to noise ratio is, well, what is the power of the input signal? We have seen this in the frequency modulation lecture. We have seen that, well, it's also easy to compute, right? Because it's a cosine. It's a cosine with some fixed amplitude. So the power will be AC squared over 2. And what will be the power of the noise? Well, this we have seen now a couple of times. It will just be N0 times BT. And this means we get it as the signal to noise ratio for FM at the input, we get the power of the signal divided by the power of the noise, which is just AC squared over 2N0 BT. Okay, so let me stop here and then continue at this part next Wednesday. So next Wednesday we will compute the output signal to noise ratio and then see how good FM modulation compares to the baseband system. Any questions? If not, then see you next Wednesday. Yeah, we'll see you next Wednesday.